Previously, we had introduced waves and observed that although there were three major categories of waves, mechanical, electromagnetic, and matter waves, that they all followed pretty much the same underlying math. And so we decided to limit our focus for the most part to mechanical waves. And then within mechanical waves, we saw that we could further divide them into transverse and longitudinal waves and observe that, again, we could represent them in the same kind of way with the same sort of math. And so we pretty much zoomed in on transverse waves, planning to talk about any differences as they go along. So with all of that as background here, I want to talk about how to describe the propagation of a wave. And there's absolutely nothing that's... It turns out that a wave can look like any function you would like. So I'm just going to draw some sort of arbitrary thing like that and say that this is a snapshot of my wave at time 0. So a snapshot means that I'm looking at the entirety of my wave. So again, here, this is my y-axis, but I'll represent this as some function d. And I'm just saying along the entirety of x at, let's just go ahead and say time 0, which I'll just note by drawing in purple. The wave at all positions looked like this at time 0. At some later time, let's say instead of drawing it in purple, we draw it in green. Let's say our wave is moving to the right. It might, our pulse now might look, say, something like this. So I'll just say that this is t equals later. And then to just think about it even a little bit more, let's pick, this blue right here should be good. There we go. I'll say that that's at t equals even later. All right. So in general, if I wanted to write a function that would describe a wave, pretty much any function will do. So I'll just say that d, where d is the displacement of my medium, is a function of both the position in the medium and the time that I'm looking at it, is just some function f, pretty much any function we like. And I'm going to write the argument of it kind of weird, but I will justify why I am doing that. So this is just any old function f. Does not matter what it is. X is my position, t is my time. So I need all of these things to have the same units. And looking ahead, we're going to go ahead and eventually we'll be invoking a theorem due to Joseph Fourier that says that I can represent pretty much any function that describes anything that actually happens in nature as an artfully chosen collection of sines and cosines. And so with that in mind, I'm already thinking ahead that the units of this whole thing are going to have to be dimensionless. It's going to have to be radians. But it can be more general than that. All we need is for this term, and this term to all have the same units, whatever it is they are, and we need the whole thing to return meters when we get done with it. But within the idea that I'm thinking ahead to sines and cosines, the usual name for phi naught here is the initial phase. And this is just the number that I need to put into the function to correctly describe whatever it is that the wave was doing at position x equals 0 at time t equals 0. So this just fixes our initial conditions. Omega in complete analogy to oscillations, it will again be the angular or natural frequency. But we'll demonstrate that that's what that is. And then this k here is not a spring constant, unfortunately. It's a thing that gets called the wave number, and you spell it all as one word. That's just some German influence there. But we can just think of it as the constant that you multiply x by in order to get the dimensions, the physical dimension, to be the same as all the other terms. Now, even more annoyingly, you'll notice I wrote minus or plus instead of plus or minus. Why did I do that? We will see in a moment the minus sign means that the wave is propagating to the right, and that a plus sign here means that the wave is propagating to the left. Honestly, I just remember it as backwards of how you think it ought to go, but I'll prove why that is. In fact, we'll just start that right now. So if we're thinking about some feature on the wave propagating, like let's pick the peak here just to make it nice and concrete. It was here at this time, then later it's at that time, later it's at that time. So in some sense, we can say that the wave is propagating with some velocity v, right? Now, how am I going to, if I think about this just from the math of it, how am I going to get this peak mathematically? I need it to be such that at time 0, when I put in whatever x was, I got this number out. Then at some later time, though, I'm going to put in a different value of x, and I'm going to put in a time of t that's not 0. And I still need that same number to come out. And then even later, I'm going to be putting in still yet a different value of x and still yet a different time of t, and I still need this function to return the same thing. The only way that can happen is that for a particular feature, in a wave, such as its crest or something like that, what we need is the argument of the function, whatever it is, to be a constant, to always be returning the same number. So it's got to be a constant. So we will need that my kx minus or plus omega t plus phi naught equals a constant. So at some later, it's at some later time t, I put in a different value of x, and all the math works out to give me the same number I had before at t equals 0, and x being over here to get me my peak right there. Y equals my peak. All right. But this will let me get the speed of my wave, because I can differentiate both sides of this with respect to time. So differentiating the first term with respect to time, k is a constant, I can pull that out of the derivative. And I'll be left with dx dt. All right, minus or plus. So for the second term, omega is a constant, I can pull it out of the derivative. And then I have dt dt, which is the fancy way of writing the number 1. And then for the third term, that's differentiating phi naught, which is a constant, so that just gives me 0. Differentiating a constant also gives me 0. All right. So dx dt, though, I can interpret as the velocity of the crest of the wave, or whatever other feature it is we're tracking. So I can say this is kv minus or plus omega equals 0. So rearranging kv, so now I have to either add to cancel the minus or subtract to cancel the plus to both sides. So give me a kv is plus or minus omega. So I eventually get that v is equal to plus or minus omega over k. And this is true in disgustingly general. And this is why we counterintuitively have to put the minus sign here to go to the right, the plus sign here to go to the left. It's just after you do the algebra, that's how it works out. The best way I can think of it otherwise is that as x increases, I need this term here to decrease to offset it in order to keep returning my peak as I move off to the right. Alrighty. So with that, we can start to think about representing the propagation of the wave. And here, what I'm going to do is I'm going to invoke a theorem due to a mathematician by the name of Joseph Fourier, which says that for any function that describes anything that would actually happen in nature, I can write that function as a carefully chosen collection of sines and cosines. And since the only difference between a cosine and a sine is the initial phase, I can just turn that into sines, which means that the only function I need to think about is the sine function. So, and a lot of waves just plain are sinusoidal, so we're good to go there. So we will say that our function is a sine times the sine of kx minus or plus omega t plus phi naught, like so. And again, this is, so we'll just let that be the case. And again, we are interpreting the minus sign there as meaning that the wave goes to the right, and the plus sign as meaning the wave goes to the left. Now, let's go ahead and draw some examples here. So let's go ahead and take a look at time t equals 0. Now, I'm going to choose an initial phase of pi over 2 just to show that it doesn't have to be 0. So I'm going to draw a snapshot graph at time 0. Remember, snapshot graph is just showing the entire wave at one instant in time. Think of taking a snapshot on a camera of, say, the string or whatever it is we're looking at. 1, 2, 3. Oops. There we go. I get 2 complete waves in here. So this is x, and since this is a transverse wave, we can say this is y, which will be equal to our d of x and t. So at time 0, at position 0, if the initial phase is pi over 2 radians, this would be the sine of pi over 2, which is 1. All right. And then we can just follow it from there. We can go ahead and draw our sine wave. Like so. Oops. There. And actually, let me be a little more clever for just a moment, since I'm having to redraw this due to bad art anyway. I want to copy that. There. And let me try drawing my sine function again. This is a, this is minus a. I'm just trying to draw a cosine, really. All right. I think that's as good as it's going to get. So that's at time t equals 0. And just to define some terms here, we can see that we have repeated peaks, and so we can define the distance between two peaks to be the wavelength of the wave. And so that is a lowercase Greek lambda. So if we go back to the special paper that we used in 3rd grade, you draw a lambda like that. That's the Greek equivalent of the letter L. So it's just another letter L for us to suggest a length. All right. Well, let's go and look a little while later. So I'll put in another one here. Oops, my bad. There. So there we go. So instead of this being at time 0, I'm going to cryptically call this time capital T over 4 for reasons that will make sense in a moment. The main point is that this is some later time. So if my wave is propagating to the right, if I put in a later time, this is going to make this argument smaller. So the time that I happen to have chosen will be the one where we actually have x equals 0 at t equals 0. And then just following along from there, there, our wave looks something like that. Now, what if we advanced by exactly that same amount of time? So we'll go ahead and put in another one here. Oops. There we go. So now instead of it being t equals 0 or t over 4, capital T over 4, we're going to call this t over 2. All right, well, we will have advanced the argument by the same amount. So if this was enough to make this whole amount here decrease by pi over 2, it'll make it decrease by pi over 2 again. So now what we'll have is a function that looks like a negative cosine here. Well, I tried really hard. Something like that. All right, let's keep the process up. So if we do another quarter of a period, so now we're at 3t over 4. It's just going to look like this, just continuing to shift over. Yeah, okay. That's all supposed to be the same height. And then finally, shift over another quarter of a wave, and we end up right where we started from. So we'll just go and put that there. There we go. But now instead of that being time 0, that is time capital T. All right, so what's going on here? Well, if I look at this point right here at position x equals 0. So I'm just going to draw a square around it each time, like this. So just think about, like, if I put a bead on the string right here, remember the bead's not going to move side to side, it's a transverse wave. So it's just bobbing straight up and down. Now what I can do is I can make a plot. And this is what's called a history graph instead of a snapshot graph. I'm going to make a plot where everything is happening at y equals 0. And I'm going to plot the displacement of this, the y coordinate, which is my displacement, as a function of time now instead of as a function of position. So everything's happening, sorry, not y equals 0, but at x equals 0. So initially at x equals 0, we are sitting up at a. So there's a there. And I'm just going to draw in a dot to represent where we are at x equals 0. At time t over 4, if we go take a look at there, at x equals 0, my bead is sitting at the origin. Or sorry, sitting at 0. Not the origin necessarily. Sitting at 0. So that's at time t equals 4. At time t over 2, my bead is sitting at negative a. Like so. Then at 3t over 4, it's back at 0. And finally at t equals t, capital T, we're back up there. And this is looking like a sine wave, and in fact it totally is. Because what we've done is we've just stuck in 0 for x, right? So this is a sine wave. Alrighty, so our sine, or in this case because of my initial phase of pi over 2, it ends up looking like a cosine, but that's neither here nor there. The point is that we are undergoing our bead is undergoing simple harmonic motion. So any point on the medium executes simple harmonic motion, and the period is capital T. All right. So that finally gets us back to thinking about how to interpret our k and our omega. So for k, k is our wave number, remember. And so what's happening here is if I increase x by lambda, I'm going to get back, I'll be at the next crest in the sine wave. Well, how much is the argument of my sine going to have to go up by? It's going to have to go up by 2 pi. So for that to all work out, I need k to equal 2 pi over lambda. And so our wave number has units of radians per meter. And remember, a radian technically isn't a unit. It's just a symbol to remind us that we're working with a dimensionless angle. And by the same token, since we've recognized that our purple bead here is undergoing simple harmonic motion, if I locked x down, x equals 0, my argument has to cycle through 2 pi once every period. So like we saw before, the angular frequency has to be 2 pi over the period, or we can write that as 2 pi f. Either way, the units are going to be radians per second. And so now we can double back and take a look at the speed of my wave. Remember earlier we found that the speed of a wave was equal to omega over k. Well, omega is 2 pi over the period. And we're going to divide that by 2 pi over lambda. So I get lambda over the period. Or the way we usually write it is v equals f lambda. So both of these are equally useful. We can say v equals omega over k, or v equals f lambda, the frequency times the wavelength. And the way we can see this intuitively is if we watch over one period. Let's mark in red, I guess. Yeah, we'll use red. So I'm just marking my crest here with an X. In one period here, so it's half a period, you can see that my crest moved half a wavelength. And then as I continue along, after one complete period, my crest moved an entire wavelength. So I could have just as easily started by saying that the speed was lambda, the velocity is lambda over t, and then got v equals f lambda from there, which again, that's usually how we write that. Now, because of these 2 pi's showing up all the time, I'll just observe that we are free to write our equation for a sinusoidal wave. We can write as, like we were doing before, d of x and t is a sine kx minus or plus omega t plus phi naught, where a is the amplitude, and that has to be in meters. Where a is the amplitude of the wave. Because k is 2 pi over lambda and omega is 2 pi times f, or 2 pi over the period t. It's actually pretty common to also write this, and this is just really a matter of personal preference. You can also write it as the sine of 2 pi times x over lambda minus or plus t over t plus phi naught. These are the same thing, so it's totally a matter of personal preference whether you want to think in terms of wave numbers and angular frequencies, or whether you want to think in terms of wavelengths and periods. Just don't mix up the two choices. This 2 pi is just me factoring out a 2 pi from each of these. So just to give some example of how we might represent a wave, let's say that we have a wave that is 3 meters long with an amplitude, of 0.5 meters, moving to the right at 6 meters per second. How would I represent that as a function here? So I can say y of x and t, or just using our more generic capital D for a wave displacement. I can go ahead and put that in. Now here, since I've been directly given the phrase 3 meters long right here, I am inclined to go and use the form that has the second form here that has the 2 pi's sitting out there. So if I use that, so let me just write that down. A cosine 2 pi x over lambda minus or plus t over t. Let's see what we can pick out right away. Right away, just from it having been said that the wave was 3 meters long, that tells me that the wavelength is 3 meters. So lambda is 3 meters. They give us straight off that the amplitude is half a meter. Okay, that's nice. They didn't tell us anything about the phase, so I am assuming an initial phase of 0, so that's why I just plain dropped it there. So really all that's left for us to do is to find the period, and then we would be good to go. So to get the period, I can say, well, the speed of a wave is frequency times the wavelength, or it's the wavelength over the period. So the period would be the wavelength over the speed of the wave. They gave us that the wavelength was 3 meters. And they told us it was going to the right at 6 meters per second. So that's half of a second. So, okay, my period is half a second. Now all I'm left to do is choose between the minus and the plus, but they said moving to the right. So that means we pick the minus sign, because remember, you pick the upper sign if you're going to the right, the lower sign if you're going to the left. So with all that, I can finally write my function as 0.5 meters times the cosine, times the sine, my bad here. All that does is change the phase by 90 degrees anyway, but I just want to stay consistent. Times the sine of 2 pi x over 3 meters minus t over 0.5 seconds. And there you go. Now, you can also obtain relations for wave speed through basically looking at F equals ma and applying it to the situation. However, what I'm going to point out is that at the introductory level, pretty much the treatment for how to obtain the speed of a wave, almost every author has to pull some sort of sleight of hand, and a proper analysis can't be done until you derive the wave equation properly in classical mechanics, in upper level treatment of the material. So my attitude is I just quote the results from a more advanced treatment. So let's say you have a wave propagating in a string. The speed of the wave in a string is, here I'm going to write t sub s just to not confuse things any more than I have to. This t sub s is the tension in the string. And this mu here is the linear mass density. Or the mass per length of the string. And I'm not going to justify where this comes from. I have done it elsewhere on the channel. I'll just assert that the derivation is pretty tedious, but that's the correct result. And the derivations that you tend to see in introductory physics texts, they tell a story that gets you to that answer, but they pull some sleights of hand along the way. So I tend to not usually pay too much attention to it. Similarly for sound, in order to find the speed of a longitudinal wave in, say, air or something like that, it involves an upper level treatment of thermodynamics. So again, I'm just going to quote the result. You can write it as gamma times Boltzmann's constant times the absolute temperature over the mass of a particle, Or if you prefer working in moles, you can write this as gamma RT over the molar mass. So T is the absolute temperature. Gamma is the coefficient of the specific heat at constant pressure, specific heat at constant volume. So just for at room temperature, gamma is 5/3 if it's a monatomic gas. And it's 7/5 if it's a diatomic gas at room temperature. Just to give some sense of what are typical speeds of a wave, for speed of sound in air, at 20 degrees C, it's 343 meters per second, and at STP, it's 331 meters per second. And in solids, the equation looks a little different, but I'll just quote a result for diamond, which happens to have a particularly fast speed of sound. It's about 12,000 meters per second. And although steel isn't as fast as that, it's a heck of a lot faster than air. So that's why if you watch all those old bad spaghetti western movies, you'd see the whole crew, the whole wagon train is progressing along, and they come up to some railroad track, and the head of all the wagons will stop everybody, and they go put their ear to the rail. They're listening for an oncoming train and taking advantage of the fact that the sound wave is propagating down the rail a heck of a lot faster than it's propagating through the air. And so the idea being that if they can't hear the sound down the rail, they'll have enough time to cross the track before the train would actually come. The other use that I'm sure you probably have run across at some point in your life, the speed of light is 3 times 10 to the 8 meters per second. So if you see a lightning strike, and it's anywhere near you, the light got to you in less than a millionth of a second from when it actually struck, typically. Or at least, less than a millionth of a second. And so we can basically say that that was instantaneous enough. However, there's a delay between when you see the lightning strike, when the light waves hit your eye, versus when the sound waves hit your ear. Now, very roughly, every 3 seconds would be about 1,000 meters, very roughly. So that's where you can do the whole thing of when you see a lightning strike and you start counting off seconds after you see the lightning strike. Every 3 seconds between when you see the lightning strike and when you hear the thunder come in corresponds to the lightning strike being another kilometer further away. So if it takes 3 seconds, it's 1 kilometer away. If it takes 6 seconds, it's 2 kilometers away, and so forth. If you prefer working in standard American equivalents, you can go ahead and do the conversions to convince yourself that you should count 5 seconds to see that that the distance was a mile. Alrighty, so I want to finish up this treatment of wave speed by asking one more pause and ponder question. So, let's say that as the wave travels along, something causes the speed of the wave to change. What I'm thinking of is, say you have a string that's tied onto a thicker piece of string. The thicker piece of string would have more mass per unit length, so there'd be an increase in linear mass density, which would drop the speed of the wave in the thicker chunk of string versus the thinner chunk of string, as an example. Or in case of a sound wave, we could imagine that it's going from one region where maybe there's a change in the mix of gas, or maybe there's a change in the temperature because of weather patterns, something like that. It caused the speed of the sound wave to change. So let's say there's some condition change to cause the speed of a wave to change. Which of the following properties of the wave changes? Does just the wavelength change? Just the frequency change? Do both of them change? Or do neither of them change? So pause the video and get back with me on that one. All right, it turns out that it is just the wavelength that changes. So the best way, or the best story I ever heard to think about that is to imagine a story of a ridiculously well-organized jailbreak. And in this story, the idea is that the prisoners discover a flaw in how the security system works. There are some cameras that are on moving mounts, and they discover that once a minute the cameras are blind to action happening in a particular part, along a particular part of the prison wall. So we can imagine then that we have a prisoner hopping over the wall in our incredibly well organized jailbreak at the rate of 1 prisoner per minute. So every minute they take advantage of this lapse in security, and they hop over the wall undetected by the security cameras. Now, let's say initially they're just plain running down the road. You can run pretty fast going down the road. And so what I've done here is I'm just noting this is where you'd be 1 minute later, 1 minute later. So, or we can think of it, this is the prisoner who hopped over the wall 1 minute earlier. This is the prisoner who hopped over the wall 2 minutes earlier, and so forth. All right. Well, you want to get off the road, so at the very least, they managed to duck onto so this is a paved road, let's say, and they managed to turn and start riding down a gravel road. You can't run as fast on gravel as you can on asphalt, so the distance you can cover in a minute is less, like so. So again, this would be the prisoner 1 minute earlier yet, 1 minute earlier yet, 1 minute earlier yet. And then finally, as they're trying to head over to their hiding spot, they have to make their way through some swampy area. You can't cover very much distance in a minute. Now, because this is an incredibly well-organized jailbreak, we have the SWAT team already sitting over here waiting to capture the prisoners and return them. So my question is what is the rate at which the prisoners are being captured? 1 a minute. You make a new prisoner every minute. At any point along the road, once a minute, a prisoner goes by, and that includes at the capture station at the end of the prisoner's escape. However, the distance between the prisoners decreased as their speed decreased. So It's the wavelength that changes, not the frequency. Alrighty. So in the next video, we will talk a bit about some more technical issues of representing waves, not too much. And then we will talk about longitudinal and electromagnetic waves for just a little bit to talk about how they differ. So we'll see you over in the next video.